Hello. It's a pleasure to be here, as opposed to teaching like I was yesterday, which was also nice. I will talk about Ramanujan graphs, complexes, and most importantly, digraphs, because you haven't heard about Ramanujan digraphs, I think. And this is actually what I'm trying to sell. This is a marketing talk. I'm trying to sell the concept of Ramanujan digraphs. I'm trying to.
How much?
At the end, you will want to. So we start with Ramanujan graphs. We have an adjacency operator of a graph. Everybody knows that. And then for a k-regular graph, the spectrum is between k and minus k. K is an eigenvalue of the constant eigenfunction, and minus k is an eigenvalue if and only if the graph is bipartite. Everybody with me so far? Good. Now, the graph is a good expander.
Not clearly better than your students, but we've seen this before.
Good. So the graph is a good expander if all these eigenvalues, except the extreme one, are close to 0. And it is a Ramanujan graph if they are in the strip of size 2 square root of k minus 1, around 0. And Ramanujan graphs are optimal. This is what we're always told, but they're not optimal. So if you take the graph, the projective plane graphs, which is the incidence graph of lines versus planes in a 3 space over a finite field, you get a k-regular graph with better spectrum. All the spectrum is square root of k minus 1, not twice square root of k minus 1. So this is better than Ramanujan. But the point is that asymptotically it is optimal. So the theorem of Alon-Vopana tells you that for any epsilon, if you try to get below the Ramanujan eigenvalue, if you try to get to that minus epsilon, you can only do that finitely many times. There are only finitely many graphs which are better than Ramanujan. I'm open to questions. No.
There is a minus little of, there is a minus little of 1. There is minus little of 1, which people often...
Where?
2 root k minus 1.
No, you just think of k as independent of the number of vertices.
Yeah, and it's going to infinity.
No, that's the finitely many.
No, it's not, there's nothing wrong with it.
Ah, okay. Can we turn this noise off somehow? Okay, because I can't hear any of you. I'm sorry. So this is fine.
No, nothing wrong with it.
Good. Thank you.
Just to explain, there is also nothing wrong with Alon-Vopana. Just there is a little of 1, which you can write there.
Okay. So the question is why 2 square root, twice square root of k minus 1? And there is a conceptual answer, which is that every k-regular graph is a quotient of the k-regular tree. And this is the spectrum of the k-regular tree. So this is an old result of Kesten. This is Kesten's PhD thesis, that the spectrum of the k-regular tree is this interval that we count as Ramanujan, that we call it the optimal expander. And indeed, this can be generalized. So for any infinite family of quotients of one graph, eventually the second eigenvalue has to go at least to the spectral radius of this infinite covering, this common covering. Now, the question is existence. And, well, the complete graph is Ramanujan, which is a nice example, also trivial. But the point is that the number of vertices is also the degree. So it's not very interesting. The projective planes that I discussed earlier are also Ramanujan, and there the degree is the square root of the vertices. So we're doing a bit better. But the interesting question is, for a fixed degree, can we construct an infinite family of Ramanujan graphs? And this is what Lubotsky, Philip Sarnak, and Margulis did independently in the mid-'80s. They showed that for a k being a prime plus 1, there are k-regular Ramanujan graphs with the number of vertices arbitrarily large. And specifically, the construction of Lubotsky, Phillips, and Sarnak is as Cayley graphs of finite, familiar, and beloved groups, which is actually very useful for applications of these graphs. And then this was generalized by Morgenstern to prime powers plus 1, also as Cayley graphs. And only in 2013, Markus Spielmann and Srivastava showed that for every k, there is an infinite sequence of bipartite Ramanujan graphs. So you have to allow the minus k. It is still open. It's still an open question whether you can do it without the minus k in the spectrum. So this is the history of Ramanujan graphs. And now I'll go a bit inside the LPS construction, because this will direct us in higher dimension. So what Lubotsky, Phillips, and Sarnak showed basically is that these 6 matrices, I'm taking a concrete example. This is, you can do it with other primes. Now I'm taking the prime 5. So we're looking for a 6 regular graph, 6 regular Ramanujan graphs. And they show that these 6 unitary matrices generate a free group in the group of unitary matrices with entries, projective unitary group with entries in Z1 over 5. And this group acts simply transitively on the vertices of the 6 regular tree. Now, once you have a group which acts simply transitively on the vertices of the tree, it is a free group, so this is how they see it's free. But the question is, where does this come from? And the answer is that this 6 regular tree is the symmetric space of the p-adic Lie group associated with the unitary, with PU2, not over, oh, that should be PU2, by the way. It's 2 by 2 matrices associated with unitary matrices over the 5 adic numbers, which is also a PGL over Q5. So you can think about whichever group you like. And symmetric space, that appeared in one of the, I think in Winnie's lecture. That's the analog of the hyperbolic plane, for example, for the group SL2R. This is a contractible space on which the group acts. And then from very deep arithmetic theorems, so incorporating a lot of 20th century mathematics, they show that these elements, when you project them modulo another number, give you a graph with the same spectrum as they had before you projected them. So, for example, let's take the number 13. Now I'm looking at these 6 matrices modulo 13. So the first one is 1 plus 2i. So what is I mod 13? So it's written, it's 8. Why is it 8? Because 8 squared is 64, which is minus 1. That's all. So all you do is really project its modulo 13, and you need to realize that I has a meaning, modulo 13. So we got the...
Also 5.
What?
Just one of them.
Yeah. Ah, there are 2. That's true. That will get you the minus 1 here, the other one. So we got the matrix 4, 11. You do the same with these 6 matrices. You get 6 matrices in PGL2 F13, and the Cayley graph they generate is a Ramanujan graph. This is the LPS construction. And you can see that the 6 here, that's the trivial eigenvalue, and then the next one is below Ramanujan. Yes, I have to separate.
You're not the first to
You
check
can
it.
kick him out of class.
Okay, so that's LPS. Why did I go into this? What? What? Yeah. Oh. So why did I go into this? Because this was the starting point for going to higher dimension. So here are Ramanujan complexes. So you have here PU2, so why not replace it with PU3 or PGL2? Let's go to PGL3. So Ramanujan complexes were defined and constructed independently by Winnie Lee and by Lubotsky, Samuels, Vishne. And I'll remark that there were also previous attempts by Ballantyne, by Cartwright, Solejuk, which also had this idea, but in a sense didn't find, today we think, the correct definition and didn't have a complete construction. And the idea is to go to the Brutitz building of a general p-adic group. So now we take a group like PGL DQP or PGLD FPT, which is the same over the field of Laurent polynomials, is very similar. And we look at the Brutić-Belting, which is the symmetric space of these p-adic Lie groups. You don't need to know about it a lot to just absorb the feeling of this. You need to know about it a lot in order to actually prove something, but basically what you want to know is that these are infinite contractible simplicial complexes. And for U2 or GL2, that's a tree. So it's a one-dimensional contractible simplicial complex, which means a tree. But now we have infinite contractible simplicial complexes of higher dimension. And the idea of the people here is that we should define Ramanujan complexes as quotient of the building, which has the same non-trivial spectrum as the building. So non-trivial here refers to the fact that for a k-regular graph, Ramanujan, we allowed k and minus k, even though they're not in the spectrum of the tree. We have to allow them. A finite regular graph will always have the k in the spectrum. So the same thing happened here. Once you have a finite quotient, there are some eigenvalues you have to allow because of finiteness, which tells you basically about the degree and the periodicity of the complex. But everything else, you want to be in the spectrum of the building, like you had for the graphs, like you had in Kesten. Now, the question here is spectrum of what? So there are many more operators. You can take the adjacency operator on the underlying graph, on the one skeleton. And this is actually what Ballantyne did. But the point is that there are more operators. So for example, both Lee and Lubotky-Samuels-Wishnek studied these operators, which are called the colored Hecke operators on vertices. So as Winnie told you, these buildings come with coloring of the vertices. And now I can define the colored adjacency. So I sum the AJ, the J color adjacency operator, sum over the neighbors whose color is my color plus J. So I only sum on some of the neighbors according to colors. But I got more operators like that. If I actually sum all the AJs for all the colors, I get the usual adjacency operator. And let's just get a feeling what happens here. So let's look at A1. So this means I sum all the neighbors of color 1 more than me. So for a graph, this is actually the regular adjacency operator, because a graph is always colorable by 2 colors. A graph is always bipartite. And all your neighbors are always of the other color. So for a graph, A1 is the usual adjacency operator. But in general, what happens is that for d-dimensional Ramanujan complex, the spectrum of this operator, this is the trivial eigenvalue. So if d is 1, which is the graph case, you get p plus 1. But then in dimension 2, you get p squared plus p plus 1, for example. And this is the non-trivial spectrum, the interesting part. So here you have the square root of p to the d times a sum of numbers of norm 1 and product 1. So if in dimension 1 you have 2 numbers, but they are reciprocals, they're reciprocals of one another. So their sum is somewhere between minus 2 and 2. So you got square root of p times something between minus 2 and 2, and this is the Ramanujan strip. But when you
spectrum on the building.
that's the spectrum on the building, and by definition on a Ramanujan quotient, yeah, because this is how we'll define. We want to have the same spectrum. Well, this is actually on the quotient. This is not on the building. This is the trivial eigenvalue. This is on the building.
2 and 0 is 1?
Sorry?
This is the factor 2 that we had?
Yeah, exactly. So the 2 in the Ramanujan comes from Z1 plus Z2, and Z2 is actually 1 over Z1, so together it's a real number between minus 2 and 2. But it's not like this anymore when you go to dimension 2. Then you have here 3 numbers whose product is 1 and norm 1, so it's somewhere between minus 1.5 and 3. And it's not real anymore also. So the spectrum is not real anymore. And also now we have something of a size up to 3 times square root of the degree more or less. So what is this 3 doing here? Now we got something which is not twice, now it's 3 times. And the question is, so why? What is special about this? And what is special about Ramanujan complexes? And one possible answer, which is due to Winnie, is you can do an Alon-Bopana theorem. You can show, this is in Lee's work, that if you look at the sequence of quotient of the building, eventually you'll have to cover this. So you cannot do better. I cannot ask for something which is smaller as long as I'm looking at families of quotients of the building. So it makes sense to call Ramanujan what I cannot do better than. So that's one answer, but from the point of view of combinatorics, it's not that, it doesn't make you happy as a combinatoric, because you want to understand what's special about it, like, combinatorially, not what do I get from this? And now the point is that this is the Hecke operators is what was studied in all of these work, but after that people started looking at other operators. For example, if you look at high-dimensional Laplacian, they don't work on vertices. They look at higher cells. So you want to look at more operators, and you want to include them in the definition. So today we define a Ramanujan complex to be a quotient of the building, such that all the operators on cells of the building have this non-trivial spectrum contained in the corresponding spectrum on the building. Because, for example, I want to be able to talk about Laplacians. And then Uriah first showed that actually Lubotsky-Samuels-Vishne construction is Ramanujan in this stronger sense. So all the operators on all cells are okay, are kosher. The spectrum is in the spectrum of the building. I don't know about the construction, about your construction, Winnie.
I think the Uri, yes.
That's also your construction. Okay, so both these constructions give you Ramanujan complexes in the stronger sense that we want once we want to talk about things which are not operators on vertices. And since we're doing high-dimensional combinatorics, this is what we want. Vertices are still dimension 0. So this is kind of a very brief history of Ramanujan complexes. But the question now is, in what sense are these high-dimensional expanders? Because this is our goal. This is what we set out to find. And it took time, but people proved very interesting results. So homological connectedness is the first result, actually, that you can put here. And this goes back to the 70s, showing that all these complexes have trivial homology with coefficients in the reals. And that goes back to Garland. And this is something that people use over and over again, the Garland's insights. Then more recent work, more modern work, is the Gromov geometric overlap. So these quotients have the geometric overlap property. Any affine map to Euclidean space, there is a point which is covered by a lot of simplices. And this was done by these 5 people for GLN, and then by Shayevra for general semi-simple group. So you can replace, I didn't say here, here. So both Winnie Lee and Lubotsky-Samuels-Vishne mostly study the building of PGL, but you can move to study building of symplectic, orthogonal, unitary, and so on. And then geometric overlap holds for all these buildings by Shai's work. And then there's work on chromatic numbers by several people here, and the topological overlap, which is much harder than geometric overlap, also by people mostly in the audience and elsewhere. But the point is, the point which I want to make is that actually all these results, which are very interesting, all these results actually apply to all the quotients of the building. We don't really need the Ramanujan. Everything written here, when you go and read the proof, you don't really use the Ramanujan. You don't use the fact that the spectrum is really contained in the spectrum on the building. You can do with something weaker. And I'm not talking about density, like Peter was referring to. Density is almost Ramanujan. I'm talking about it's more property T. It's the fact that in higher dimension, everything is an expander, basically. And then we want to ask, okay, so in what sense Ramanujan tells us something? And this does appear in more recent work. So Perez-Lubetsky actually used Ramanujan to do the optimal mixing that Peter was telling us about yesterday. And then with Eyal Lubetsky and Alex Lubotsky, we generalized this to higher dimension to have similar results for Ramanujan complexes. And this time we really need Ramanujan complexes. We cannot do with general quotients and property T. And similarly, the works of Kang and Lee and Kang Lee Wang that we heard about very recently, and of Amitai Kamber on zeta function also ask, in a sense, they ask about the specific eigenvalues. They want to, the Riemann hypothesis which appears there is really about Ramanujan. So I want to understand what's special about Ramanujan, and the machinery that I will use for that is digraphs. So now I'm digressing to digraphs, and I'll define a Ramanujan digraph, and then we'll connect everything together. We'll see why Ramanujan graphs and Ramanujan complexes and Ramanujan digraphs are all connected very nicely. So now we have a digraph. If anybody doesn't know, this is a directed graph. So now the edges are directed. And the problem with digraph, and the reason that nobody likes them, is now that the spectrum is complex. The adjacency matrix doesn't have to be symmetric, so the spectrum can be complex. But still, if I have a k-regular digraph, and for me k-regular is in k edges going in and k edges going out at every vertex, k is in the spectrum as an eigenvalue of the constant function. And again, I have minus k if the graph is bipartite. This time, I can also have k times other square roots, roots of unity if my graph is periodic. So for 3 periodic digraph, I'll get k times third root of unity, and so on. But I call all of these eigenvalues trivial, everything which comes from periodicity. This is all trivial. And I'll say that digraph is Ramanujan if its spectrum, so now it's in the complex, and so except for the trivial eigenvalues, everything else is in the disk of radius square root of k. Not twice square root of k, not twice square root of k minus 1, square root of k. And we'll see why. Now, the big problem about digraph, apart from the spectrum being complex, is that even if I understand the spectrum, maybe the adjacency matrix is not diagonalizable, so the spectrum doesn't tell me a lot. Or it could be diagonalizable, but not unitarily diagonalizable, and then arguments using inner product will break down because your basis is not orthonormal. And this is the real problem, that the spectrum doesn't tell you a lot in the digraph case. And I'm just mentioning here, because I'm following Winnie and Ming Tuan, that this can also be formulated in terms of zeta function. So you can look at the zeta function, which counts, so now it will be directed cycles. So now gamma is a directed cycle in your digraph. This brackets mean up to starting point. And you take this product over all the prime directed cycles. And this becomes the determinant. So this is Hashimoto, Sunada, Kotani, and also there are other people who realized it in the context of dynamic systems before that, I think. And then the digraph will be Ramanujan in this sense if and only if it satisfies a Riemann hypothesis, meaning that there are no zeros with real part in the strip between 1/2 and 1. So here's one reason that this makes sense. But I'll not go into zeta function. So fear not. Now, why digraphs are nice? Actually, all of these things, random walks, branching processes, digraphs, are all the same in the sense that they all describe the same thing. I have a set. I'm trying to describe a random walk on the set. I just need to tell you where can I go from every point. Or branching process, where can I branch? Or digraph is where do I go from this guy? So it's just different languages to talk about the same thing. And the digraph language is very nice. And another thing which for me is the same is Markov chain, actually. Except that now in Markov chain you're allowed to put weight. So it would be something like a weighted digraph. But these are all different languages to talk about dynamics on a set. And with every random walk rule or branching rule, I can associate a digraph which tell me how this walk looks. So for a rule W on a complex X, and it can be on vertices of the complex edges, triangles, and so on, I associate a digraph which describes this walk. For example, if I look at the Hecke operator that I was describing, and I look at the digraph, it will give me a digraph on the vertices, which is just a subgraph of the skeleton of the original complex. But I can do it on higher dimension cells. So if I look at a graph and I take the non-backtracking random walk on a graph, this is another branching rule or random walk that we like. It actually defines a digraph on its edges, because in a non-backtracking random walk, you have to remember you're at a vertex, but you also remember where you were before that. So you actually remember two vertices all the time. So it's actually a walk on edges. So in this case, the corresponding digraph will have as vertices the directed edges, and as edges, so two directed edges will be connected by an edge if they concatenate to a non-backtracking path in the graph. And I get a new graph, a new digraph, and simple random walk on this digraph really corresponds to non-backtracking random walk on the original graph. Let's do it again. So I have the digraph of non-backtracking walk of what? I have the digraph of non-backtracking walk on the graph G. Its vertices are the directed edges, and its edges are non-backtracking path. I do it again because I have a picture. So this is the graph, and it's not directed. But now for every edge, I put two vertices corresponding to the two directions I can choose on this edge. And now I connect them by this rule. So from this directed edge, from this edge directed in this direction, I can continue here or here. So I can go here or here. So this is the digraph that, and then I forget the original graph. So this is the digraph corresponding to non-backtracking walk on a graph. And the first theorem that connects these things appeared a lot this afternoon. That's the Hashimoto theorem. So we saw it as an equality between zeta function, but it can be stated as a connection between the spectrum of a graph and the spectrum of its non-backtracking digraph. And it said that for every eigenvalue of the graph, you take this eigenvalue plus minus square, and these are the eigenvalue of this digraph. So is the statement clear? And in addition, you have a bunch of plus minus ones coming in, appearing with the Euler characteristic, that the number of edges minus vertices. And now it's a nice exercise to look at this thing and show that this thing is is bounded by square root of k if and only if lambda is in the Ramanujan strip. So what we get here is that my graph G was a k plus 1 Ramanujan graph if and only if its non-backtracking digraph is a k Ramanujan digraph, k regular Ramanujan digraph. So this, in a sense, is the first theorem about all these things. And we're trying to generalize this to higher dimensions. Well, this gives you a complete connection. You just need to work out when is this thing beneath k. You do the computation and you get it exactly when lambda is between minus 2 squared k minus 1. Yes, it's nice to do that. I like this computation. It shows you that there is sense in things. So, and also you can ask about the directed graph corresponding to non-backtracking walk on the tree. And you get the same thing. So you get the square root of k and these plus minus 1.
With or without the invariant of the circle?
No, without. Yep. Now, the big problem here is that this digraph we got is not a normal, its adjacency matrix is not normal. Let's do that. So I take a vertex, then I go, I do A, and then A transpose means going backwards. So I need to choose an edge and go opposite the direction. So this is A transpose. It gets me here or back where I started. But I can get here with A transpose. But if I do A transpose A, I get to different places. A transpose A transpose A. I get there, and A transpose gets me here. So it's not a normal operator. So spectral analysis fails. And the big breakthrough of Peres-Lubetsky is to show that, actually it's almost normal in the sense that it's not unitarily equivalent to diagonal matrix, which is normal. It's unitarily equivalent to a 2x2 block matrix. So if you go stand really, really far away, you think it's normal. That's the biggest breakthrough in this paper, I think, because this part was known before. They gave a new proof for the Hashimoto formula in order to deduce that. It's very beautiful. And the point is that this really replaced normality, and they are able to do analysis and get all the nice results that they get there. Now, what happens in higher dimension? So the first thing we tried when we start looking at this in high dimension, we looked at non-backtracking random walk on a Ramanujan complex and on the corresponding digraph. And it's not a Ramanujan digraph. The spectrum is not contained in the square root of the degree. So you don't get the same thing for free. However, you have other walks that do. So the geodesic edge flow, which is the same thing as what Winnie was describing when she was, in Winnie's term, that's the one-dimensional gallery. You go, so now you walk on edges, and you go from an edge to another edge. This is no backtracking. But now you also require that these three edges together will not be a triangle in the complex. So we call it geodesic because we're saying, oh, if I have a V.
We cannot close it.
Exactly. We don't have this shorter way around. So we only allow walking here if there's no shorter way. And then it turns out that this walk does give you a Ramanujan digraph. So specifically, the spectrum was computed by Cayley and Wang of this walk on Ramanujan complexes, or equivalently on the building. And it's very nice spectrum. You have the circle of radius square root of k, and the circle of fourth root of k. And then they have other operators like that on SP4 and GLN. That's also work with Fang and Wang. The names are very complicated to remember.
Not to speak of the
Pardon. I should also also make the remark that Fang's first name is Yang. Yeah. So when you see, so we have Yang, Fang, Wang, and Kang, and Winnie. So they have other operators with this property. So we set out to find. We wanted to generalize this, and this property of having the spectrum in the right place was very important. So the question is, why do certain walk give you this? Why didn't we get it from non-backtracking random walk, for example? And we were quite surprised that we managed to answer this question, because at first we just set out to prove something like Lubetsky pairs for some operators on higher dimension. And we were quite surprised that we managed to give a complete answer. And the answer is that the corresponding walk has to be what we call collision-free. So a collision-free digraph is a digraph where every two vertices have at most one path between them. So there are no two paths that start somewhere and end at the same point. It's not the same thing as a tree. So for example, if you take the non-backtracking random walk on a tree, and that's the picture we saw earlier, so let's pretend this is a three-regular tree, but now I'm looking on the non-backtracking random walk. I have a lot of cycles here. So this is, I do 1, 2, 3, 1, 2, 4, 5, 6. 1, 2, 3, 4, 5, 6. There are a lot of cycles of size 6. No, I allow both directions. This is why I'm saying it's not a tree. But this does have this property of collision-free, the non-backtracking random walk. So if I start with, for example, here, and I'm doing non-backtracking random walk, from here I can go either here or here. And then from here I can go to these, and I'll continue here. And from this guy, I'll continue here. So I'll never meet myself. So non-backtracking random walk on a tree have this property, even though it doesn't look as a tree in itself. And so the point is, if I have a finite digraph, I cannot have this property. If it's finite, I have to meet myself eventually. But what we're looking is on the branching rule, or the random walk on the cover, on the building. So the theorem is that if I have a rule, a random walk rule, which is collision-free on the Bruetitz building of any semi-simple algebraic group, This is what surprised us, that we managed to prove it for any semi-simple algebraic group. And we have a Ramanujan quotient of the complex. Then the digraph described by this walking rule on the quotient is an almost normal Ramanujan digraph. So Ramanujan digraph means that the spectrum is in the disk of square root of the degree. And this almost normal is this property that the adjacency matrix is unitarily similar to a block diagonal matrix with blocks of bounded size. We don't care about 2 by 2, but we need a bounded size if we want to do spectral analysis. So this is what we had. And I should point out, how much time do I have?
15 more minutes.
15? 15. 50. I should point out that I want to compare this with Winnie Lee's and with Ming Chuang Kang. Is he here? Hi. Work. So it's very interesting because we had their work as a starting point, and their work goes through a very detailed analysis of either the representation theory or the structure of the building. And they get things like this. We cannot get something like that. We cannot tell you the spectrum is this circle and these points which they are able to. But the point is that if you're only interested in the question if the spectrum is inside this disk or also outside, we have an argument which circumvents all the representation theory which gives you that. And that's the part that surprised us, that we managed to do it without going in, like somehow bypassing huge machinery that we thought we'll have to use at some point. And we only have the argument which tells us that we're inside the disk, but not where the poles and zeros are like they have. So it's something different, but we were surprised that we were able to get that far. And then from that point it continued like Peres-Lubetsky. So almost normal Ramanujan digraphs have this optimal sharp cutoff and almost diameter. And another thing we have to say, if we want to understand something about these complexes, we need to show that there are collision-free walks. So there are collision-free walks. So if you take a Ramanujan complex of dimension d, there are collision-free walks on the cells of every dimension except 0. There is no collision-free walk on vertices, but on edges, triangles, and so far there are. And we understood which are these collision-free walks, and now from Ming Chuan lecture, I learned that this is called a straight element. That we didn't know the name, but we had exactly the same condition. We need the Weyl length of the power of the element to be the right length. And this corresponds to collision-free walks. And then we have the Riemann hypothesis, the cutoff, the diameter, everything that we get from this concentration of the spectrum in the Ramanujan disk. So this is that project. But from that point, I became a bit obsessed with these Ramanujan digraphs. And Alex and Eyal didn't, I couldn't get them excited about that. They said, you just gave a name to something. It's not, you can't do that. But I tried to convince them that there is something interesting, so I continued looking at this. And one thing that Noga Alon showed me is that for digraph, you don't have an Alon-Bopana theorem. There are De Bruijn digraphs, very annoying digraphs, and their spectrum is K, which is, they're K regular, and the spectrum is K for the constant function, and everything else is 0. And you can put as many vertices as you want. So you don't have an Alon-Bopana theorem. But the point is, these graphs are very far from diagonalizable. And it turns out that if you add this almost normality, it doesn't matter which block size you use. As long as your block size is globally bounded, there is no infinite almost normal family of K-regular digraph, which is better than Ramanujan, in the sense that I cannot get to the disk, the Ramanujan disk minus epsilon. So the thing is, the almost normality thing, what I'm trying to sell basically is that, yeah, digraphs are ugly, but once you have this almost normal feature, they're okay.
Are you proving this by going to the universal cover or by this argument of Nili?
No, I'm using Alon-Bopana for graph. I'm taking, the argument is basically taking my digraph, looking at a high power, then transpose to a high power. This is a symmetric digraph. Then I apply Alon-Bopana and go back. No, it doesn't have anything to do with a specific universal cover. So, this, and another nice feature, so this is joint work with Ron, we have this Chernoff bound, which is very useful for walk-on expanders. Once we have almost normal directed expanders, we have the same thing. So it means if we have a function on the vertices, let's say to the interval -1, 1 with some 0, and we take a random walk on a digraph, and we look at the average of the function on the vertices we visit, and we ask how much it deviates from the mean, which is 0, and it decays exponentially in the length of the walk. So this is the same thing we know about expanders, which is very useful. We can do it for directed expanders under the assumption of almost normality. And then this constant depends on the almost normality. So somewhere you have to pay, but it's only a constant. And a corollary from that, which is nice, we also get from this a Chernoff bound for non-backtracking random walk on regular graphs. So now you can take any expander, and I want to understand the Chernoff bound for non-backtracking random walk. I can translate that by putting the function at each vertex. I put its value on all the outgoing edges, and then I do my this random walk on the digraph, which correspond to the non-backtracking random walk on the original graph. Use this and get the result for the non-backtracking walk on the graph. And similarly for higher dimension. And another application of this is joint with Tali Kaufman is a notion of powering for Ramanujan complexes. So if you have an expander, you can take a power graph, which means that you take the adjacency matrix, raise it to a power, and call that a new graph. And this is the same thing as saying I'm constructing a new graph whose edges are paths in my original graph. The point is it's hard to do that for a high-dimensional expander, to do something which somehow will take a power in the high-dimensional expander. We tried to do that for some time, and the basic thing is that when you go to this power, you're actually looking at the sphere of a larger radius in your complex, and these spheres are not expanders. That's the basic problem. They're far from being expanders, but once we do this expansion along geodesics, so these are the same geodesics which appear in the geodesic flow, we do get we do get from this powering operation a high-dimensional expander again. Okay, so these are a bunch of applications. Do I have time for another one?
8 minutes.
8 minutes, that's good. So this is actually my favorite. So this is the question of Cayley graph. So we know that Ramanujan digraph exists because we had Ihara Hashimoto, which tells us that once you have a Ramanujan graph, you look at the digraph corresponding to non-backtracking walk, you got a Ramanujan digraph. But can you make a Cayley graph, Cayley digraph, which is Ramanujan? So this came out as an unexpected corollary of work with Peter Sarnak from last year, which was about quantum computation, something completely different. But in that group, we constructed specific elements in the unitary group on 2 variables, which has a more interesting action on the tree than the LPS group. So we had a finite group, finite subgroup, and an element, another element. And this finite subgroup fixes the origin, fixes the root of the tree, and acts simply transitively on its neighbors. And the second element is an involution, and it flips an edge. So here's the picture. You start with an edge, E0. This tau flips this edge, so it takes you here. And the elements of C takes you to the other edges leaving this vertex. This guy is tau and then C, because you flipped and then rotated. And once you have such element, it's easy to show that the group they generate acts simply transitively on the directed edges of the tree. So here's one example, which has this is an element of order 5, which acts simply transitively on the neighbors of the origin of the 5 regular tree, and this matrix is of order 2 and flips an edge. And phi is the golden ratio. And then let's look what happened when I take elements of the form C tau, where C is not the identity. So I have C which is not the identity, so it takes me somewhere here. And then tau flips this edge, so it has to take this guy somewhere here. So I got here. So from this edge, I got to this edge. Now I do it again. I apply some C, so it rotates me somewhere here. And then again, tau, it will take me here. So what these elements describe is exactly the non-backtracking random walk from this edge onward. And the point is, so I take this S, these generators, and then they, as I multiply more and more elements from S, I'm just describing non-backtracking random walk on the edges of the tree. But the basic thing is we need to have a lattice which acts simply transitively on the edges in order to describe this non-backtracking random walk in arithmetic terms. Once we have them in arithmetic terms, we use again Ramanujan conjectures and everything around it. So the Jacquet-Langlands correspondence, and we get that if we take the same element and project the modulo some prime, we'll get a finite group with the same spectrum as we got upstairs. But the point is, my elements do not correspond to vertices anymore, but to edges, and I'm describing the non-backtracking random walk. And we know this its spectrum is the square root of k, not twice. And so here's the statement, that if I take the Cayley graph of this S mod Q, I get a graph with the spectrum contained in the spectrum of the non-backtracking walk on the tree. And this made me very happy because it's something you can check, unlike a lot of things that you encounter in mathematics. So we went and checked that. So these are the elements I showed you earlier. And they act on the edges of the 5 regular tree coming from these p-adic fields. And I project the modulo 31 here, for example, and I get a Cayley graph with this spectrum. So it's a Cayley graph on PSL2 F31. Just a second, and here's the trivial eigenvalue. Here are the Ramanujan eigenvalue, and also the 1 minus 1 coming from the Euler characteristic. Yes?
We don't have anything inside the circle except
Right.
the trivial ones.
They're not trivial. These are the Steinberg, if you want to give them names. Is that the Steinberg and the twisted Steinberg, I think? I was very happy when I saw this picture because, up to that point, I was sure we're making it up. Nobody can check it. Jacquet-Langlands.
I'm just asking, maybe you should make the definition that all eigenvalues except these.
No, so no. So this is the point. That's why I actually showed you a lot earlier this picture with the 4th root of k here. So when I'm looking at other operators, I'll get this, for example. I'll get there in a minute.
That's fine, but now you're looking on a particular operator.
Okay, so
Operator maybe is,
no, I'll answer you in a second. So this is, for example, and actually I put this, bless you, I put this because 5 is not a prime plus 1. This is why I like this example in particular, because it's coming from a number field which is not Q, and what happens here is that the norm of 2 in this number field is 4. This is why we got 5. And from our work, we get a K-regular Cayley Ramanujan digraph on PGL2FQ with these degrees. So 2, 3, 4, 5, 7, 11, 23, and 59. What's special? That's exactly the thing. So the point is that all these numbers are prime powers, and these number plus 1 is a size of a subgroup of symmetries of a Platonic solid. So it actually happens inside U2, also in a number field over U2. And we actually need to find out this number field. And all of that still doesn't guarantee that everything worked. Then we need to go check by case that indeed the corresponding Platonic group acts simply transitively on the neighbors. And there are 2 cases where it doesn't, so they don't appear here. 10 doesn't. Even though A5 has a subgroup of order 10, it's not here because 10.
9.
9 is not here. Yeah. So it's not a tautology, but in most cases it did. There are only 2 cases where it didn't work for some reason. And the nicest is the 59, which is the full icosahedron. So this is PGL2. And we're bounded here because the size of a finite group inside PU2, even in the reals, is bounded. So we cannot go beyond 59. The largest subgroup of PU2 is finite subgroup of PU2 is of size 60. Oh, yeah, you're right, you're right. But, yeah, they're bad. And now the thing is, you can go further if you leave the number field case and go to the function field case. So actually, I can do it for every D. I can give an almost normal Cayley Ramanujan digraph structure to PGLD FQ because, and now I don't take FQ as a quotient of the numbers, but a quotient of Laurent polynomials. But this is, I think, in contrast with the case for Ramanujan graphs, where if you try to generalize LPS to high dimension, you get these Ramanujan complexes. You look at the adjacency that you get on the Cayley graph, you get this 3 times square root of p that we saw earlier. Things get worse. But if I look at digraphs, I'm still at a normal digraph. I'm still at a Ramanujan digraph even when I go to higher dimension, to PGLD. The only place where I pay a price is this almost normality. What I will get is that when I go to PGLD, my adjacency matrix will be similar, unitarily similar to a matrix with blocks of size d by d. But when you do the analysis, you see that the size of the blocks is really doesn't affect you almost at all. And then you get from this all these results on diameter, cutoff, and so on for finite groups of higher rank. So for PGLD, which we can't, as far as I see, get from the symmetric generator. So this is why in my opinion, now digraphs are nicer than graphs, because I cannot do that with graphs. Get the same optimal result for PGLD. And the basic idea here, am I done? So I'll just say, the basic idea is that I can construct an arithmetic lattice which encodes this geodesic edge flow for the building of PGLD. And then use everything, so Ramanujan, Jacquet-Langlatz, which in this case is due to Badulescu, and so on, and get Ramanujan digraphs. So let's go here.